To see the earliest moments of the universe, astronomers needed to look past the visible spectrum and into infrared light. They built the James Webb Space Telescope, specifically designed to capture those deeply stretched wavelengths. But when it powered on, the observations didn't match the timeline we expected. Instead of a slow, gradual assembly of matter, the telescope captured light from massive, fully formed galaxies existing when the universe was incredibly young. JWST uncovered a strange population of objects, often called little red dots. One specific system, spotted just 700 million years after the Big Bang, appears to host a black hole weighing roughly 50 million times the mass of our Sun. These detections reveal a specific timeline flaw in our models of black hole growth, pointing towards a missing mechanism in the early universe. In the standard model, a black hole is born when a massive star runs out of fuel and collapses. These stellar remnants start out extremely small. To reach millions of solar masses, they need billions of years to slowly pull in surrounding gas and merge with others. This chart compares that standard growth rate against what we are actually observing. The bottom slope shows the billions of years required for a typical black hole to grow. The steep vertical line shows what it takes to hit 50 million solar masses so quickly. There simply aren't enough years available. These objects had to begin their lives already massive, as heavy seeds. If these seeds didn't come from dead stars, we have to look for a mechanism that predates stars entirely. We have to look back to the violent, explosive energy shifts that occurred moments after the universe began. Immediately following the universe's initial expansion, it went through a violent transition called preheating. This was the moment the energy stored in early cosmic fields was rapidly converted into the first radiation and particles. It was an explosive process. Smooth energy fields filling space suddenly began to oscillate, and those oscillations pumped immense energy into microscopic ripples. This graph models how that energy behaves. When the ripple is weak, the energy moves in predictable, closed loops. But as the energy intensifies, the system enters a state of mathematical chaos. The graph scatters, showing a state where microscopic differences trigger drastically different outcomes. Within that chaos, energy cascaded down to smaller scales. Those tiny ripples amplified, eventually condensing into towering, tightly packed spikes of extreme density. If an area of space becomes dense enough, gravity takes over. These microscopic, hyperdense clumps could collapse directly into primordial black holes, long before the first stars ever formed. This mathematical model presents the early universe as a chaotic forge, a brief window where violent energy fluctuations could instantly stamp out tiny black holes across the cosmos. But there is a strict physical limit to what this process can build. It's called the horizon mass. At any given moment, the universe has a maximum distance where things can physically influence one another. Only mass inside that specific, causally connected region can gravitationally collapse. During the preheating phase, the universe was incredibly small and incredibly young. The horizon mass was microscopic. Any black hole forged in this exact era could only weigh about as much as a paperclip. This diagram illustrates the problem with those microscopic seeds. At the bottom is our 1-gram primordial black hole. At the top is the minimum mass required to explain the giants seen by JWST. There is a gap of at least 36 orders of magnitude between what the chaos could build and what we actually see. Furthermore, Stephen Hawking demonstrated that black holes slowly lose mass and evaporate over time. A black hole that weighs only a few grams wouldn't just sit there waiting to grow. It would evaporate almost instantly. Even if chaotic energy successfully created these black holes, the laws of physics ensure they were too small and lived too briefly to explain the massive objects in our deep space observations. There is one speculative mathematical loophole that attempts to bridge this gap, known as primordial black hole reformation. The idea requires the early chaotic storm to produce an overwhelming swarm of these tiny black holes. Because matter dilutes slower than radiation as the universe expands, this dense population would briefly dominate the total energy density of the cosmos. Under those extremely crowded conditions, the tiny black holes wouldn't have time to evaporate independently. Instead, fluctuations within the swarm itself would cause the clusters to gravitationally collapse inward, merging thousands of tiny bodies into a heavier second-generation black hole. This second generation would be massive enough to survive evaporation entirely. They would persist through the darkness, serving as the massive starter seeds capable of eventually anchoring the giant galaxies we observe today. Right now, this reformation process is a mathematical toy model. It proves the math works in an isolated test, but it is not a confirmed simulation of our actual universe. To be accepted as part of the cosmic timeline, this theory must align with data from the cosmic microwave background, gravitational wave frequencies, and the sequence of structure formation. Any viable theory mapping the early universe must pass a strict three-part test. It has to define the exact scale where the chaos occurred. It has to identify a surviving physical relic. And it must mathematically bridge the enormous scale gap without violating known physics. This early chaotic storm left behind microscopic debris that may explain the massive giants JWST is seeing. Proving its existence would resolve the timeline gap of the infant universe.